Very good evening, dear students. So in today's class, we are going to discuss a new topic. In fact, in continuation with what we have earlier discussed related to network synthesis. In the last class, we had talked about LC network synthesis using Foster and Cover forms. So today, in the last topic on this topic of network synthesis, we will talk about lossy network synthesis. Lossy network synthesis means we will have the presence of resistance in our network. Okay, so as you can see on the slide also, the title of the slide is lossy networks RC oblique RL. So in case of RC, we will have resistance and capacitance, and in case of RL, we will have resistance and inductor. So since resistance is present, so obviously uh, it will be a lossy circuit, not a lossless circuit as it was in your LC networks. Fine. Though Foster form, cover forms, we have understood in details. We have seen their examples also. That way, it will not take much time when we cover RC and RL, because all the concepts we have already discussed in detail. All that is required is we have to replace one of the components with the resistance. So in case of RC, your inductor has been replaced with resistance. In case of your RL, your capacitor has been replaced with the resistance. And more or less the same things we will be discussing as we have talked about in the previous classes. All that is required for understanding is you have to correlate today's class with the previous classes. So if you are able to correlate, then it will be a child's job to understand that thing in a clear fashion. So let us move forward. So we start with our lossy network synthesis. So as you can see in LC network synthesis also, we started with Foster forms of network realization. So here also we will start with Foster forms. We will study about Foster forms of RC networks and Foster forms of RL networks. Okay, and we all know that Foster forms are of two types, Foster 1 and Foster 2. So that way, for RC network, we will have Foster 1 and Foster 2. Similarly, for RL networks also, we will have Foster 1 and Foster 2. So let us start with Foster 1 form and Foster 2 form of RC networks. So if you look at the slide carefully, on the left hand side, I have shown the way we have synthesized our network in previous classes. Like your ZS has been splitted into Z1 and Z2. Okay, so like ZS can be represented as Z1 plus Z2, and then we had extracted Z1, and then by using continued fraction approach, we had solved for Z2. Okay, and this was, you can say, the kind of ladder representation that we had seen in the previous class. Okay, so here like if you remember the Foster representation, so there for LC network we had inductor in the place of resistance. So those inductors have been replaced with resistances here. See, okay, so this is your Foster 1 form of RC network. In case of LC network, what we used to have, we used to have inductor here, we used to have inductor here, and we used to have inductor here. So those inductors are replaced with resistances. Okay, rest of the things are, you can say, similar. This is the series representation. So in series we had all the elements in series, and this combination was earlier a combination, parallel combination of L and C. Now it is a parallel combination of R and C. Okay, so this is how your Foster 1 form of RC networks look like. So students, you please correlate this RC network of Foster 1 form with your LC network of Foster 1 form. Okay, and if you are able to recall, in case of Foster 2, we had parallel representations for the circuit, and apart from that, here we had this earlier classes we had L and C in series. Here we have R and C in the series. Okay. And here we had inductor earlier in the LC network. Here now we have resistance. So all the inductors have been represented or replaced with resistances here. Okay. And as a result, you get foster two forms of RC networks. I think now you are able to correlate the foster forms of LC network with your foster forms of RC network. Is it fine? So, and you also keep these forms in your mind so that we are able to discuss further. Let us move forward. So now we exclusively take foster one form of RC networks. Okay. And since students, as you can understand that we will realize these forms of network realization with the help of network functions. And if you remember in the network functions, we had written those network functions in the partial fractions using your Laplace transform. And if you are able to recall, in case of foster one form, if we had inductor here, then this last element was represented by, if you can recall, it was say HS. Okay. So now since it is a resistance, for resistance, the Laplace transform remains the same. So that's why it has been represented as A infinity. This is a capacitor. So the impedance function for the capacitor is 1 by CS. Okay. 1 by CS. So that's why this part of your driving point impedance is representing this series capacitor. This R infinity is represented by A infinity as series resistance. And now you see here this part. This part is the parallel combination of resistance and capacitance. Okay. So let us first try to solve this portion, and we will try to obtain the equivalent impedance of this parallel RC network. So if we do that, you see here, we'll be able to get this function. So your RC parallel circuits impedance will come out to be 1 by C multiplied with 1 by S plus 1 upon RC. Okay. So this is the final result. It has been shown, but if you try to solve this, this is nothing but parallel combination of R1 and C1. And in case of Laplace, your R1 is represented as R1 and your C1 is represented as 1 by C1S. Okay. So you apply the parallel combination formula, that is your R1 multiplied with 1 by C1S. Okay, it is multiplied. This is the numerator part, and in the denominator we add them. The way we add obtain parallel combination of resistances, same thing we have applied here after applying Laplace transform. So this is the parallel combination of R1 and C1. If you solve this, you will get this. Okay. So this has been specially represented in this form so that we are able to correlate this representation with the partial fraction approach. Okay. So this is the ZRC, and now see, if you look at this thing carefully, 1 by C is nothing but a constant. Say that constant is A1. Okay. And then multiplied with, this is 1 by S plus 1 by RC is also some constant. Okay. So you can represent it with say sigma 1. So it becomes A1 by S plus sigma 1. This is A1 by S plus sigma 1. Similarly, the second part will give us A2 by S plus sigma 2. Third, A3 by S plus sigma 3. Okay. So, and so on. So the intermediate parts of this RC networks are represented by A by S plus sigma. Okay. The series capacitor is by A naught by S, and your the final last element resistance is represented by A infinity. I hope this representation is clear to you. If you remember, in case of LC network, this intermediate part was represented like this, like it was of the form S square plus omega square. I hope you remember that. We had shown that it was represented by the poles on imaginary axis, whereas this is S plus sigma 1. That gives us S is equal to minus sigma 1, which is nothing but this pole is a real pole and it lies on the negative half plane. Okay, so this is the representation. Now if you compare this circuit diagram with this partial fraction representation, you can easily see that, see, what is this? 1 by C naught S, and 1 by C naught S is equal to A naught by S. That means C naught is equal to 1 by A naught. Similarly, if you correlate this A1 by S plus sigma 1 with this series combination, sorry, parallel combination of R and C, you get C1 is equal to 1 by A1. Similarly, if you compare, see what is sigma 1? Sigma 1 is 1 by R1 C1. So that gives us R1 is equal to A1 by sigma 1. And what is R infinity? It is A infinity. Similarly, R2 will be A2 by sigma 2. Similarly, R3 will be A3 by sigma 3. Okay. So this is how we represent our Foster 1 form of RC network. I hope it is clear to each and every student. So students, now let us move to next slide. So here I am telling you the properties of RC driving point impedance, RC, because we are talking about RC network for Foster 1 form of representation. And see, for the time being, I'll advise you that you just memorize these properties. And if you practice numericals, you will be able to at once understand that these properties are outcome of nothing but the analysis of network functions. Okay. So here I'm telling you to memorize these, and otherwise you could also derive these properties by looking at the network function carefully. Okay. One thing we have already seen just now in the previous slide, I told you that what are the poles? S plus sigma 1 is the pole. That gives us the value of pole as minus sigma 1. I told you that this minus, it shows that your pole lies on the negative S plane, negative axis. Okay. So see, the first property is poles and zeros are lying on negative real axis. Okay, that is property number 1. Then second property is that your poles and zeros will alternate on the negative real axis. Alternate means if I draw S plane, if you have a pole here, you will get 0 here. Then you will get a pole here. Then you will get a 0 here. This is the meaning of alternate. One by one, alternately. Poles are alternate and then zeros are alternate. Okay. And then the third important property is that the residues of the poles. Okay. Residues of the poles means when you substitute the value of the poles, the value of the network function that you get, it must be real and positive. Okay. And I have underlined this property. The purpose of underlining this property is that as you move from RC to RL or from RL to RC, this property is going to change, and this property you also have to basically notice, so that you are able to understand by looking at the network function only whether it is the RL representation or the RC representation. Okay, so for Foster forms, Foster first form, okay, of RC driving point impedance, the residues of the poles are real and positive. Keep this thing in mind. And the fourth property, you, for the time being, you simply memorize. You may not understand this thing fully. So once we are complete with the chapter and thorough practice of the numericals takes place, then we will be able to understand this property number 4. Right now, I'm not deliberating on this property number 4. Okay, so these are the properties that you have to keep in mind. So this is Foster 1 form of RC network. Now let us move to Foster 2 form. So this is the Foster 2 form. From impedance, we have moved to admittance, because you can see that this is a parallel network, and parallel network can be easily represented by using admittance. So here we have driving point admittance function. And in the previous slide, we had driving point impedance function. I hope you are able to understand this. Okay. So we are now representing our Foster 2 form by using driving point admittance. See, this is driving point admittance. We have expressed it as a sum of individual admittances. So what are individual admittances? This is resistance. So resistance is nothing but a constant value in the Laplace representation, which is nothing but B naught. This last element is a capacitor. So admittance of the capacitor in Laplace domain is Cs. So C is a constant. So it has been represented with this. So this is the last element, which is nothing but Hs. Now we are left with this branch, which is a combination of series, combination of resistance and capacitor. Okay. So as I told you in the previous case, here, since it is a series combination, so the equivalent impedance for this series combination will be R1 plus 1 by C1s. But we do not want impedance here, we want admittance. So for admittance, it will be reversed. And that's what it has been done. So this admittance is equal to 1 by Z. Okay. So 1 by Z means 1 by R1 plus C1s. So this is R1 plus 1 by C1s. I hope it is clear. And if you solve this, the form of representation that you will get is this one. That is B1s divided by S plus sigma 1. For second branch, B2s by S plus sigma 2, and so on. So this is the intermediate representation of this series combination of R1 C1, and this is the first element, and this is the last element. And if you basically compare it with the circuit representation, what do we get? You will get Ri is equal to 1 by Bi. Okay, this you already know what is B naught. B naught is nothing but R naught. Okay, and this H gives us nothing but C infinity. Okay, and now we are left with R1 C1. Okay, so what will be R1? R1 is 1 by B1, and what will be C1? C1 is 1 by sigma 1 R1. Okay, and that you will be able to easily derive, as I did in the previous slide, by solving this yi. Okay, I hope this is clear. It is very, very simple. Now you see here, in the last slide, when we were discussing properties of Foster 1 form of RC network, I had told you that the residues of the poles, they must be real and positive. Whereas in case of Foster 2 form, see, the residues of the partial fraction expansion, they are real and negative. Okay, so if you obtain residues, they will come out to be negative in case of Foster 2 form, whereas in case of Foster 1 form, they will come out to be positive. And students, the more you practice, because now it is going to be a bit confusing for you people, because the things are related in such a, a complex manner that you may get confused. So you'll have to practice hard so that you are able to clarify those minor differences in the various representations. Okay, so please practice as much as you can. So this is your Foster second form of your RC network. So now we will look into one or two examples so that you are able to appreciate what we have discussed till now. So let us move. Before taking example, let me first complete this Foster form of representations. Okay, so what we have done in the previous slides, we have talked about Foster representations 1 and 2 for RC, and now we will discuss the Foster representations of RL. Okay, so Foster representation of RL, Foster 1 representation of RL network, it looks like this. See, here you remember LC representation of Foster 1. Okay, when you represent RL, there your C has been replaced with R. So wherever C was present, it has been replaced with R. So now you see, here we used to have series capacitor, it is represented by R0. Here we had capacitors, that is represented by R1, R2, R3, like that. And this is nothing but inductor as usual. Okay, so if you look at Foster 1 of RC, you see this was Foster 1 of RC. Okay, now we have Foster 1 representation for RL. So this is your Foster 1 representation of RL network. Okay, so obviously since it is a series combination, so we will use driving point impedance function. Okay, so now let us write the equivalent Laplace representation. R naught is a constant, so we will have a constant A naught. Now this is RL combination, RL parallel combination. Okay, we will just derive how does it look like in the form of Laplace. First let us see the last element, that is L. So its equivalent representation is Ls, which is represented as A infinity S. So this is the last element, this is the first element, and this is the intermediate element. And how do we represent intermediate element? This is parallel combination of R1 and Ls, because now we have inductor. So we have to solve this. So if you solve this, you get this R into Ls divided by R plus Ls. And if you further represent in the expression equivalent to partial fraction, see, we have rewritten it like this. R in, we divided by L in numerator and denominator, we get this, and then we represent this. So you see, this is nothing but this one. So your intermediate elements of this RL network has been represented with A1S by S plus sigma 1. So here also you can see that S plus sigma 1 is in the denominator part, which gives us S equals to minus sigma 1, means your poles lie on the negative half of your sigma axis. Fine. And if you compare your circuit with this partial fraction, you can find out the values of various circuit components, which gives us R naught is, A naught is nothing but R naught. Okay, and your A infinity is nothing but your L. For intermediate elements, if you compare this A1S by S with this one, if you compare, what is A1? A1 is nothing but R. So A1 is R1. Okay, and what is sigma 1? Sigma 1 is R1 by L1. So see, sigma 1 is R1 by L1, and L1 is nothing but A1 by sigma 1. So this is how we can represent our circuit components in the Foster 1 form of RL network. See students, if you follow a uniform approach, okay, if you follow the concepts that in case of series combination we have to follow, or we have to follow driving point impedance. In case of impedance, it is the sum of impedances. You write impedances for the individual branch. Okay, and then you can develop that. If you try to cram things, then you may fall into a pit and you may not be able to understand things in a clear fashion. So stick to the basics, stick to the concepts, try to understand things, practice a lot. So this is the Guru mantra for going through this chapter. Otherwise, you will get confused. Definitely, you will get confused. Okay. So this is your Foster 1 form of RL networks. Now let us move forward. So these are the properties of RL driving point impedance. Okay, so for RL, you can see here that the residues are real and negative. So this thing you have to memorize. Okay, and this is exactly same. Your poles and zeros, they lie on the negative real axis. Your poles and zeros, they alternate as it was done in your RC also. Okay, but this thing you have to uh, basically notice and understand clearly. Fine. uh, I think this is RL na. Yes, this is RL. So by mistake here I have shown the RC. It will be this one only. You have to represent this one. Okay, so here it will be R. Okay, here it will be L. Okay, then here also you'll have inductors. So then it becomes the RL representation. Fine. So now we move to Foster 2 form of RL network. So as we discussed, Foster 2 is a parallel combination. So here we will consider driving point admittances. Okay, so in case of parallel network, admittances are simply, you can say, summation takes place. So let us see the admittance of L naught. It will be 1 by Ls. So 1 by Ls is equivalent to B naught by S. The last element is a resistance, which is a constant. So we have a constant H here. Now we have to see the admittance of this series RL combination. So we have to find out whether it is equal to this or not. So let us see that since it is a series combination, so its impedance will be uh, R1 plus L1S. Okay, and then admittance will be 1 by Z, that is 1 by R plus Ls. So this is what I am telling you. So your admittance for this branch is 1 by R plus Ls. So this R plus Ls, so if you take L common from denominator, what do you get? You get 1 by L divided by S plus R by L. Okay, and now you compare here. So if you compare, what do you get? Your B, fine, your B1 is equal to 1 by L1. Okay, so here also your B naught is equal to 1 by L naught, B1 is equal to 1 by L1. Okay, similarly, your sigma 1 is equal to R1 by L1. Fine. So this is how you can calculate different values and represent your RL network using Foster 2 representation. I hope this thing is clear. And in this case, the residues at the poles of YS, they are real and positive. Okay. So I'll advise you to cross check also these things once again from the book regarding residues, whether they are real and positive somewhere, real and negative somewhere. I may also have made unintentional mistake because things are a bit confusing and repetitive. Okay, so please understand that. So now let us talk about numerical example 1. Fine. So I hope now the Foster forms of representation for RC network and for RR network both is clear to each and every student. So students, this is numerical example 1 of your RL representation using your Foster 1 form of representation. Okay, so since Foster 1 form, we are given with your impedance function, driving point impedance function. Fine. So it is represented like this: twice of s plus 1 into s plus 3 by s plus 2 into s plus 4. Okay. So now again and again I was talking about the residues. So here first let us talk about the residues. Okay, and also talk about the poles and zeros. So if you look at the poles are at s is equal to -2. Okay, because poles comes from the denominator. So s equal to -2 and -4, these are the poles. Okay, and what are the zeros? Zeros, that is your jets. Those are your -1 and -3. So one thing is, all poles and zeros, they are negative and they are real. First point. Second point is they are alternating. Like -1 is 0, -2 is a pole, -3 is a 0, -4 is a pole. So they are alternating. Okay. I hope you are now clear with this, that your poles are alternating on negative real axis. Okay. Now another thing is, we are saying the residues are negative. Okay, residues are negative means, like for the poles, you substitute the value of pole now. Okay, so what is pole? S equal to -2. You substitute s equal to -2 in this function. If you do that, uh, when you put s equal to -2, you do not consider the corresponding term here. If you do that, then see, 2 into s plus 1, -2 plus 1 is -1. Okay, -2 plus 3, that is your 1. Okay, then -2 plus 4, that is 2. And what is the total value? It gives us negative. So that is the meaning of your negative residues. Fine. So I hope now all of you are clear of the negative residues. Fine. So now let us obtain the partial fraction representation. So what we have done, see, one more thing you see here. In the numerator and denominator, are we missing something somewhere? No. Okay. If you study about, you know, the properties of these network representation, though I am saying that residues are real but negative. Okay. So if you take the residues of ZS, they will be real and negative. Okay, but if you take the residues of zs by s, okay, then those residues will become positive. So here in this numerical, see, look at this thing carefully. Instead of zs, what we are doing, we are taking zs by s. Okay, zs by s, so means we are dividing both sides by s. So zs by s, so one s has also been put here. Okay, so that thing may be a bit confusing, but right now bear with this thing, because as you look into more examples, you will be able to understand this thing clearly. So instead of solving for zs, we are solving for zs by s. Okay, in a way this is the same thing as this, because we are dividing by s on both sides. We are dividing by s here, we are dividing by s here also. Okay, so if you you know, obtain the partial fraction for this one, that is zs by s, you have three factors. One is s, another is s plus 2, another is s plus 4. And these k1, k2, k3 are the constant. We have studied partial fraction in Laplace transform. Now we have to obtain the values of k1, k2, k3. And k1, k2, k3 are nothing but the residues of zs by s. Okay, so if we want to obtain k1, we will multiply the entire function with s and substitute s equal to 0. See, we are substituting s equal to 0. If we multiply this with s, this s and s will be cancelled and you will be left with this. There is no s here because that s has been cancelled. And if you substitute s equal to 0, you get 3 by 4. So the value of k1 is 3 by 4. Similarly, if you want to obtain k2, you have to multiply entire function with s plus 2. In that case, s plus 2 will be cancelled and you will have other terms like this, s into s plus 4 like. Now we substitute s equal to minus 2. If you do that, you get the value of k2 as 1 by 2. Similarly, if you want to obtain s plus 4, k3 corresponding to s plus 4, then similar procedure will be followed and we get the value of k3 as 3 by 4. Okay, so students, what we have done, we have obtained the partial fraction approach for the zs by s instead of zs here. Okay, so and you can see here that these terms, they are of the form a by s plus sigma. Remember, such kind of terms we had. So in case of your RL network, let me show you. See, no, Foster's second form, I think. See, a by s plus sigma, such kind of thing is there. Fine. So we have got the residues. Now let us move forward. So now what we do, we multiply both sides by s. Okay, so this is what we get. See, we have substituted the values of k1, k2, k3 in this expression. So if you do that, it will be 3 by 4s, then 1 by 2 into s plus 2, then 3 by 4 into s plus 4, and then we again multiply with s to remove this s. So if you do that, you get this 3 by 4 plus s by 2s plus 2, this one. Okay, and now what we have done, we have represented this zs in the form of partial fraction and we can now identify elements directly. This is a constant and we know that constant represents nothing but resistance. So what we have done, we have obtained this R naught, constant one. Fine. Now you see this one. What is the form of this? S upon 2 upon s plus 2. Now let us see whether such form was in Foster 1 or Foster 2. See, in Foster 1, what we had, A1 S by S plus sigma 1. So if you compare, see, A1 S by S plus sigma 1. So what is A1? A1 is 1 by 2. Okay. So if you compare with that and you find out the corresponding value for your L1 and R1. Okay. So your L1 is nothing but A1 by sigma 1, which comes out to be 1 by 4 Henry. Okay. So your L1 is nothing but 1 by 4. Okay, and A1 I told you, your R1 was your A1, which gives us 1 by 2 ohm. Similarly, from this, you get these two values. That is your L2 is nothing but A2 by sigma 2, you get 3 by 16. Then for R2 is nothing but A2, which gives us 3 by 4. Now, how about this one? Where is this L infinity? So if you look at this carefully, we do not have any component with the value, say, we do not have any value, say 4s or 5s or of the form hs. We do not have any such component, means that component is missing. Missing means you have short. So we have only three branches here, resistance, then this second one, combination of R and L, and similarly this one. So this is your RL representation of Foster 1 form of the network. And see, more or less almost for the 90% part of this numerical is related to whatever concepts we have. discussed. Okay, so this is your RL representation of Foster one form of network. Fine. Now let us move to second numerical. So this numerical is related to Foster 2 form of RL representation. So this is our admittance, uh, driving point admittance function, which is represented like this. Fine. So what we have done here, we will try to solve it. Okay, so we have simplified these multiplication terms. This is what we get. Okay, now we have to obtain the partial fractions for this. Okay, so if you solve it using partial fraction, you will get this one: 1 plus a by s plus 3 plus b by s plus 5. Okay, so now we have to obtain the values of a and b. So these will be obtained in the same fashion as we obtained in the previous numerical, that for obtaining a, we'll have to substitute s equal to minus 3 by first multiplying with s plus 3. So this is, we have substituted for s equal to minus 3, we get a equal to 3 by 2. Then b we have got by substituting s equal to minus 5, and its value is 1 by 2. Okay, so once we have got a and b, we get this representation. This is nothing but summation of various admittances. This is also admittance, this is also admittance, this is also admittance. Okay, now since this is a constant, so this will be a resistance. So we have a resistance, this is resistance. Okay, now again we do not have any admittance component of the form 1 by ls. We do not have any such component. It means this inductor part will be missing from the final representation. Okay, let us see in the next slide. See here. So this was what we got in the previous slide. If you solve it clearly, you'll get this representation. And if you compare with the expression that we have obtained, this one is the resistance, which is this one. Okay, so R infinity is 1 ohm. Similarly, if you calculate for R1, this R1 comes out to be 2 ohm. Then L1, it comes out to be 2 by 3 ohm. Similarly, R2 and L2 comes out to be your 10 ohm and 2 Henry respectively. And since we do not have any form of for any component for this one, so obviously this is your missing. We do not include that. So this is your RL representation for Foster, since Foster second form. Okay, so admittance function was given, so that's why it was clear that we have to go for second form. And by looking at the expressions, we can basically identify whether we have Foster 1 representation or Foster 2 representation, or RL representation or RC representation. Okay. So students, after discussing this numerical of RL representation for Foster form, now we move to cover representation. Okay, so since we have seen Foster 1 and Foster 2 representation for both RC and RL, similarly, we also need to look into cover 1 and cover 2 representation for both, again for RC and RL. Okay, and now you will feel that the real confusion takes place. Okay, so that's why I have purposely, put these slides in very sketchy way, and I have simply put the direct things for that, so that you get some time to assimilate the things, and you are able to clarify your confusions. Okay, so try to recall what we discussed in the cover forms yesterday. In the cover forms, we had talked about three things. We had identified first element, we had identified last element, and then we had used the continued fraction approach. Okay, so these three things we did. So similarly, for RC network and RL networks also, same kind of thing will take place for cover 1 as well as cover 2. We will have to identify first element, we will have to identify last element, and we will have to use continued fraction approach. Okay, so same thing will take place more or less as we have also seen in Foster forms. The only difference will be that your inductors and capacitors are replaced with resistances. Okay, in either of RL and your RC. Okay, so let us see. This is our cover one form of RC network. So here you can see that your inductors are replaced with the resistances. So we have R1, then C2, R3, C4, and this is Rn minus 1, and this is your Cn. So these are our last elements. This is your first element, and these are your intermediate element. So as I told you yesterday also, that in case of cover representation, we have ladder type of network. So you can again see here that we have ladder type of networks here in your RC cover form representation. Okay, if you are able to recall this, since this is impedance function, we have Zs is equal to R1. This is R1. If you remember yesterday, we had an inductor here. So instead of R1, we had represented, we had written here a Z1. Okay, and Z1 was nothing but Ls. So now since we have only resistance, we have directly written R1 here. And then if you remember, I had told you we will invert and then write things. So what we have R1 plus parallel arm 1 by y2 corresponding to this, plus 1 by, we'll have we had Z3 yesterday. Instead of Z3 we have R3, then plus 1 by then y4, and so on. Okay, so I hope you are now able to correlate things. So this was our cover one representation. Now how to identify first element. Okay, so for cover one form of RC network, the first element will be either R1, okay, as we are showing here, and then if R1 is absent, the first element will be C2. These two things will take, like if R1 is absent, then your network will look like this. It will start with C2, then you will have resistance, then you have a capacitor, then you again have like this. Okay, such kind of thing which take place, and this resistance part has been removed. Fine. So how will we be able to know whether we have to remove R1 or not? So what we have to do, yesterday I told you the procedure. We have to substitute S equal to infinity, and once you put S equal to infinity, if it is constant, okay, it will be, if it is a constant, for S equal to infinity, if Zs is constant, then R1 is present, and if Zs is 0, then R1 is absent. Okay, so obviously very clear, because resistance is represented by a constant value. So if constant value is present, resistance is present. If constant value is 0, it means resistance is absent. This is first element. Then for last element, uh, what we will have, we will substitute S equal to 0. When we substitute S equal to 0, if our Zs approaches infinity, okay, then last element will be capacitor. Okay, capacitor. Fine. And if for S equal to 0, Zs is constant, in that case, your capacitor will be absent and only resistance will be there. Capacitor will be absent. It will be short like this. Otherwise, both will come, R and C. In this case, both Rn minus 1 and Cn will be there. Here, your Cn will be absent. Okay, so I hope this thing is this procedure is clear. Rest of the things will remain same as we discussed in the previous class. Okay, so this was cover one form for RC network. Okay, now let us move forward and try to identify that how does cover one form of RC network look like. So now cover two form of RC network. If I show you previous slide, here we had RC like this. And in cover 2, we have CR, CR, CR like this. So reversed, things are reversed. Okay. So wherever resistance was there, capacitor has come, and wherever capacitor was there, resistance has come. You can memorize it like this. So if you do that, again, this continued fraction representation is the similar as we have explained in the previous slide. We have Z1 is equal to 1 by C1s, okay, plus, then this is the parallel arm. So 1 by 1 plus 1 by R2, because here we had admittance. Okay. See in the previous slide, what we had admittance here. So admittance for R is 1 by R. That's why it is here. And you continue like this. So this is the driving point impedance representation. Now we have to identify the first element. Okay. So for first element, we have to substitute S equal to 0. Okay. So if you substitute S equal to 0 and ZS tends to infinity, then your first element is C, means this capacitor will be present. And if for S equal to 0, ZS gives us constant value. Constant means this capacitor will not be present. You'll have first element as resistance. So C1 is absent and R2 is present. Now we come to last element. For last element, we have to substitute S equal to infinity. For S equal to infinity, if ZS you obtain is a constant, then since you have got constant, obviously last element will be a resistance. And if for S tending to infinity, your ZS gives you 0. ZS gives you 0 means your last element will be absent. Last element is absent means only this capacitor will be present. This will become short. This is how your cover 2 form of RC network. So we have seen cover 1 and cover 2 of RC networks. Now let us see cover 1 and cover 2 of RL networks. This is your RL network. So see, correlate it with RC, cover 1 RC. In cover 1 RC, what we had? RC, RC, RC. Similarly, here things have changed. In cover 1 form of RL network, we have LR, LR, LR like that. Okay. And this is the representation. So for L1, it is SL1 plus 1 by, now things have reversed, 1 by R2. This is admittance. And we continue like this. Okay. So this is your cover 1 form of RL networks. Fine. So here, now again, we have to identify the first element and the last element. So for first element, when will be your L present? L will be present if you substitute S equal to infinity and you get infinity. So if both are infinity, you have L1. Okay. And if your S is tends to infinity and ZS is a constant. So if you have a constant, then L will not be present and first element will be R2. So this is how we identify. You'll have to memorize this thing particularly, that in which case first element will be present, in which case last element will be present. This is a bit confusing. So practice will make you perfect in this direction. So now let us look at the last element. Last element is Rn. So this Rn will be present when you have to substitute for last element S equal to 0. So for S equal to 0, if ZS gives you constant, then this resistance will be present. If for S equal to 0, you get 0. Okay, it means your last element does not exist. Means resistance does not exist. Only inductor will be there. Fine. Then let us move to cover 2 form of RL network. So see, in cover 1 form of RL, we had LR, LR, LR. In cover 2, we have RL, RL, RL. So this is, simple technique to, memorize and identify these representations of the network. So this is again continued fraction representation for driving point impedance. All that is required is we have to identify the first element and the last element. Here, the first element is resistance. So for that, you have to substitute S equal to 0. If for s equal to 0, Zs is a constant, then resistance will be present. If for s equal to 0, Zs gives you 0, then obviously R1 is absent and the first element will be L2. Now, for first element, you have substituted s equal to 0. For last element, you will substitute s tending to infinity. For s tending to infinity, if Zs gives you constant, that means uh, I think there is a mistake here. If it is a constant, then I think Rn minus 1 should be present. Okay. Uh, I'll have to cross check it. Okay. So for the time being, you assume that, yes, correct, correct. Just a minute. Yes. If s tends to infinity, then Zs is a constant. Okay. So Zs is a constant means last element is inductor, but before that, uh, you know, n minus 1th element is Rn minus 1. Okay. So means if for s tending to infinity, Zs is a constant, this Rn minus 1 will be present, but last element is Ln. So that's why Ln is written here. Ln is there. Along with that, obviously Rn minus 1 will be there. Okay. And for s tending to infinity, if Zs is 0, fine, then this Rn will be absent. Okay. Sorry, Rn minus 1 will be absent. So this is how your last element will be identified here. But I'll again uh, ask you to cross check it once again from the book so that you are able to get the correct answer to this. Okay. So this was our cover 2 form of RL network. So students, with this, your cover 1 and 2 form of representation for RL as well as RC network synthesis is complete. And rest of the approach or the methodology to solve numericals is exactly same as we did in the previous class for cover form representation. Okay. I hope all of you have understood this lossy network synthesis for the case of RC and RL network, and again for the case of representation in terms of Foster as well as your cover. Okay. So with this, your unit 3 is over, your network synthesis part is over, and in the next class we will discuss the new topic. So I stop here.